Hello, good afternoon everyone. So welcome to the second class for public key cryptography. So in the last class what we did was we had an introduction for cryptography in general, and we also seen where public key cryptography actually fitted in. So that was the first part of the talk, and in the second part of the talk what we actually looked at was some number theory basics which were required for understanding the RSA crypto system. Okay, so what we will do today is we will actually continue with that number theory basics, and we'll also look at the RSA crypto system, and we will then look at how RSA would be typically implemented on systems, and then we will look at some of the attacks on RSA. So in next week's class, we will further look into RSA, more attacks on RSA, and analyze RSA much in a much more detailed way. And also, we'll be looking at other crypto systems like the crypto systems based on the discrete logarithm problem, which we had introduced in the first class. And we will also look at some applications of these public key crypto systems on digital signatures. Now, if time permits, we will also have a very brief introduction to elliptic curve cryptography. Though going into much more detail into ECC, that is elliptic curve cryptography, would possibly require another course. So that is the plan for today as well as the next class. So let's start. So before we go into more details, we'll review the mathematics or the number theory which we actually started last week, and it is actually very important that you understand this number theory, because without understanding these few basics, it will be almost impossible to appreciate the RSA crypto system. Okay, so just a minute. So the background. So what we did previously was we actually introduced the concept of modular arithmetic. Okay, so we had defined something like A congruent to B mod M would mean that that when or rather that means when M when A divides when A is divided by M and B is divided by M, they happen to leave the same remainder. Okay, so we also denoted various other aspects of this. For example, we said that since A is congruent to B mod M, therefore M divides A minus B. So what we mean by this is that if you subtract A minus B, it will be perfectly divisible by M, and will obviously have a remainder. In such a case, it will have a remainder 0. Right? Another thing which we actually said was that because of this particular congruence, we can actually write something like this, that A will be equal to some constant times M plus the remainder B. Okay, and we had looked at some examples in the last class. Now, special importance for us came when we actually had the remainder of 0. So for example, if A divided by M leaves a remainder 0, we gave the notation as M divides A perfectly, right? Or we can also represent this to be equivalent to A congruent to 0 mod M. Okay, Another thing which we actually got introduced is the concept of GCD. So we define GCD as the greatest common divisor. So suppose you had two numbers, say for example A and M. The GCD of A and M, which we denote as, let us say, D, is such that D divides A and D divides M. Also, D is the largest such a number which divides both A and M. Okay. Now again, the important or the special case occurs when D happens to be 1. When D equal to 1 or the GCD of A and M equal to 1, we say that we call A and M as co-prime or relatively prime. Right? Okay. Now, the third thing we actually looked at was something known as the Euler-Torsion function. So suppose we had something called M, that is, for example, this M. So the Euler-Torsion function, which we represented as phi of M, denotes the number of integers less than M, which is also co-prime to M. So for example, we took the case of phi of 9, and we said this phi of 9 equal to 6 because less than 9 there are 6 integers which have a GCD of 1 with respect to 9. Okay, so in the last class, if you refer back, we had also enumerated all the possible values, and so the special case for us, and what we also seen last time was that there were certain properties for this phi of M, especially if M happens to be the product of some numbers, say for example P into Q, then phi of M would be represented as phi of P into phi of Q. Further, if P is prime, then we also found out that phi of P is equal to P minus 1. So using this, we had actually derived some other more sophisticated things, but for RSA, this is what is important. And another very important theorem which we actually looked at yesterday was called the Fermat's little theorem. So what we said was that suppose we had this number some A and some M such that the GCD of A and M is 1 in some sense. It means that A and M are co-prime or relatively prime to each other. Then we said that A to power of phi of M is congruent to 1 mod M. Right? This is a very, very important theorem for us. And as we've seen earlier, if M happens to be prime, then phi of M is equal to M minus 1. So A to power of M minus 1 is congruent to 1 mod M. Right? So this is possibly the most important theorem which we'll be actually using several times today. So let's take a small example of this. Let's say that M equal to 5, which is a prime, and for ease of understanding, let's say that A equal to some small number, say equal to 2. Then we know that phi of M is phi minus 1, that is 4, and therefore A to the power of 4 mod 5 should be congruent to 1. So what is this? So remember that A is 2, so we can just put 2 here. So 2 to the power of 4 is 16 mod 5 So when you divide 16 by 5, it leaves a remainder 1. So we can actually write something like this, right? So please remember this thing because it's the most important theorem which we will be actually looking at today, or which will be actually coming up several times today. Okay, so another thing which we actually looked at was the inverse of an element. So again, by definition, if a GCD of a comma m is equal to 1, then there exists some element b such that a into b mod m is congruent to 1. Okay, so uh, b is called the inverse of a. So this b is going to be a very unique element with, for a. So b is called the inverse of a and denoted a inverse or a minus 1. So we actually have something like a into a minus 1 mod m is congruent to 1. Okay. So if we, from the modular arithmetic rules that we have seen previously, so we can actually write this, or just for notation's sake, let me just keep this as a into b, where b is the inverse of a modular m is congruent to 1. So if we can apply the modular arithmetic rules that we have seen earlier today and also in the last class, so we can actually say that m divides a minus b, or we can actually say that m into k, some constant, plus b will be equal to a. Sorry. That's a mistake there. So we can actually say that m divides a into b minus 1, and also we can say that mk plus 1 would be equal to a into b. Okay. Now another thing which we actually looked at yesterday was this thing to compute GCD and the inverse. Compute GCD and the inverse. The inverse is actually known as the multiplicative inverse of the element. We are of, and so we would not require this particular algorithm too much today, but just to recollect, uh, computing the GCD was done with an algorithm known as the Euclidean algorithm, where it actually takes two numbers a and m and computes the GCD to be equal to, say, d. Now, especially if d equal to 1, the extended Euclidean algorithm, that is an extension to this Euclidean algorithm, was used to actually find the inverse of a modular m. So then if d equal to 1, then the inverse can be computed using the extended Euclidean algorithm. Okay, the way it actually went was that we obtained something like this: a into b plus m into something n will be equal to 1. So the extended Euclidean algorithm showed that we could actually achieve two numbers b and n such that a into b plus m into n equal to 1. So given this particular equation, we could actually take mod m on both sides, and therefore we will get a into b mod m plus m into n mod m is equal to 0 because it's some m into n is some multiple of m. So we get this is congruent to 1, and therefore we are able to obtain this element b such that when it is multiplied by a will give you 1. Therefore b is the inverse of a. Okay, so now the next thing which we are going to start today is again is another thing known as the Chinese remainder theorem. Okay, so this algorithm we'll be using to understand RSA mode better, and in fact it is actually used in several cases to actually implement RSA in a more efficient way, especially during the decryption of RSA. And also what, as we will be seeing later on today, it is actually used to show the correctness of RSA. That is actually used to prove that the RSA algorithm is indeed correct. So so let's look at the Chinese remainder theorem. Or you could shorten it for CRT. So we will not go into the proof of this theorem, but we will just take it as just a rule. So let us say we have say some numbers, say some co-prime numbers m1, m2, and m3, such that all these numbers are co-prime. So what do you mean by this? It means that GCD of m1 comma m2 is equal to GCD of m2 comma m3 is equal to GCD of m1 comma m3 is this, and this is equal to 1. Okay, so we have this m1 and m2 and m3, and let m, capital M, be the product of these three numbers. That is capital M is m1 into m2 into m3. Now suppose we have this and we are given a system of equations of this form: x congruent to ai mod small m1, x congruent to a2 mod m2, and x is congruent to a3 mod m3. So what the Chinese remainder theorem states that this set of congruences has a unique solution. The above set of system of congruences has a unique solution modulo m mod capital M. Okay, and let us see how to actually go about finding the solution for x. To apply CRT to find x. Okay, so the first thing is that we are going to define define these terms called m1 equal to capital M divided by small m1. That will be m1 into m2 into m3 divided by the small m1. So the small m1 gets cancelled, leaving only m2 into m3. And similarly, we could also define m2 is capital M into m2, which is m1 into m3, and we can also define m3 to be equal to capital M by m3, which is equal to m1 into m2. Okay. Next, what you will first notice is that GCD of mi comma m small mi is equal to 1 because is equal to 1 because in fact we are quite certain that we have actually eliminated the small m1 from this capital M1, and therefore the only factors of this capital M1 is M2 and M3 respectively. Okay, now since the GCD of Mi and small mi is equal to 1, therefore these two are co-prime, and therefore um, this capital Mi has an inverse, a multiplicative inverse modulo Mi. So in other words, there exists a Yi such that capital Mi into small yi mod Mi is congruent to 1, right? So Yi is the inverse of this multiplicative inverse of this capital Mi, and essentially it is this, right? Now, so if you actually take this equation and multiply it by A of I, we get A of I is congruent to AI Mi Yi mod Mi. And note that this two multiplied together is equal to 1, and therefore we can actually write something like this. On the other hand, so this is one thing. On the other hand, what we actually see is that GCD of Mi comma Mj will be equal to Mj, where j is not equal to I, right? This is because obviously by the way we actually define the capital M's, we actually have a term. For example, capital M1 is a product of small m2 and m3. Therefore, the GCD of M1 with M2 will be small m2. Okay, so we actually have that Mj divides Mi. So in other words, so M so 0 is congruent to A I M I Y I mod Mj. Okay, so from this we can now define the Chinese reminder. We can actually use this to actually show that the Chinese remainder theorem can be used to solve x in the following way: x congruent to a1, or rather ai mi yi mod mj, where I is actually varying from 1, I is varying from 1 to 3 in this particular case. So let us see a particular example of the Chinese remainder theorem, and we will see how to solve this system of equations using the CRT. So let's say that we have to find the value of x which solves this particular congruence, x congruent to 2 mod 3, x congruent to 2 mod 4, and x is congruent to 1 mod 5. So first of all, you notice that this 3, 4 and 5 are relatively prime to each other, and therefore we can apply the Chinese remainder theorem. So we will first of all define that M1 equal to 3, M2 is equal to 4, and M3 is equal to 5. Now by our definition, we will compute the capital M to be equal to 3 into 4 into 5, and that is equal to 60. Now we will then define the smaller terms, that is M1 to be equal to M2 into M3, and this is equal to 20, and M2 in a very similar way will be equal to 3 into 5, that is 15, and M3 will be equal to 3 into 4, that is 12. Now as we've seen before, GCD of 20 and 3 is 1, and therefore we can actually be able to find an inverse of 20 modulo 3. So we are actually searching for this yi, which is multiplied when multiplied by, or rather in this case by 1 when multiplied by M1 mod 3 should give me 1. Okay, so where M1 is 20. So in this case we can actually see that y1 to be equal to 2. So if you actually look at it, we see that 2 into 20 mod 3 is 40 mod 3, and this is congruent to 1. When divided by 3, it leaves a remainder 1. In a similar way, we see that GCD of 15 and 4 is 1, and therefore y2 m2 mod 4, where y2 is the inverse of m2 mod 4 should be 1. So if you actually try to solve this, you find that y2 will be equal to 15 inverse mod 4, and that will be equal, that you can actually find that out to be equal to 3. So if you look at it, 15 into 3 mod 4 is 15 into 3 is 45, mod 4 is again congruent to 1. Now in a similar way, we can actually find y3 m3 mod 5 to be congruent to 1, and we will get this y3 to be equal to 3 again. So you see that 3 into 12 is 3 into 12 is 36 into 36 mod 5, this is congruent to 1. So we have found the three inverses, y1, y2 and y3, and we also have these individual m1s, m2 and m3, and let us now apply the Chinese remainder theorem to solve the value of x. So by the Chinese remainder theorem, x will be it will be this value 2, that is a1 y1 m1 mod small m1 plus a2 y2 and m2 plus a3 y3 and m3, the entire thing mod 60. Okay. Now so this is 2 into 20, 2 into 20 into 2 plus a2 is 2 into m2 is 15 into 3 plus 1 into 3 into 12 mod 60. So this would be equal to 206 mod 60, which will be equal to 26. So now you can actually verify that when you plug in 26, so you have that x equal to 26 is the solution that we obtained from the Chinese remainder theorem. So if you actually substitute the value of 26 in all these three equations, you will see that it indeed satisfies all the three congruences. More precisely, you will see that 26 when divided by 3 would leave a remainder of 2. Similarly, 26 when divided by 4 leaves a remainder of 2, and 26 when divided by 5 leaves the remainder of 1. Okay, so this essentially is an example of CRT, and to actually summarize it, what we have done is that we have been able to solve a system of congruences of this form, that is, you have x congruent to a1 mod ai mod mi, and we are able to solve the congruence of this form, and found that this is equivalent to actually having this or solving this of equivalent to this mod capital M, where capital M is the summation of or the product of M1 into M2 and M3 and so on. Okay, so this is a very important theorem that we will be using today at least a couple of times, and the important thing is this to actually remember is this final equivalence which we get over here, which states that if you want to actually solve a particular system of equations which are modular some co-prime numbers like m1, small m2 and small m3 and so on, so that would be equivalent to actually solving the equation of the form x congruent to some ai mod capital Mi. Actually, that would be the summation over here. Okay, so with this we will first some set of questions before we later on go into the details of the RSA algorithm. So this is these 6 things that we have actually, or 7 things that we have actually shown over here is sufficient for understanding most of the course that follows. So these 7 things have to be totally clear, and if this is clear, then we will be able to actually understand RSA in a much better way, and we'll be able to appreciate the security guarantees that the RSA algorithm gives, and also we'll be able to actually understand the various proofs for RSA and so on. Okay, so I will take a set of questions right now before we go further in detail about the RSA algorithm. Oh, okay. So if there are any questions about this mathematical background, then you can ask it now, because from here we will actually be going into the RSA algorithm and going further into the details about the proofs and so on. Okay, question. So please tell Fermat's theorem again. So just to recollect, so there are essentially 2 things which are involved in the Fermat's little theorem. First of all, we actually use this term known as the Euler-Toshen function, which is denoted as phi of m, and this phi of m counts the number of integers which is less than m and relatively prime to m. That is, it is the number of integers which is less than m and has a GCD of 1 when taken with respect to m. Okay, so we had taken the example of phi of 9 to be equal to 6, and previously we had also seen that phi of 26 is 12. So you can actually verify that there are 12 integers which are less than 26, which is also having a GCD of 1 with 26. For example, you could see that the numbers 3, 5, 7, 9, 11, 13 is not there, 15 and so on have a GCD of 1 with respect to 26. Now Fermat's little theorem states the following. So suppose you have some number a and m which are relatively prime to each other, and therefore they have a GCD of 1. Then the Fermat's little theorem states that if you take a and raise it to the power of 5 of m, and the result will be congruent to 1 mod m. So we had taken a particular example where m equal to 5 and a equal to 2. Then phi of m is the numbers which are relatively prime to 5. That is, since 5 is a prime over here, so the numbers which are relatively, the number of numbers which are relatively prime to 5 is 4. That is like 1, 2, 3 and 4. So all of them have a GCD of 1 with respect to 5. So phi of 5 is 4. And you try to apply Fermat's little theorem over here. You get 2 to the power of phi of m, that is 2 to the power of 4 mod phi, should be congruent to 1. So you can actually verify this, that 2 to the power of 4 is 16. 16 modulo phi is 1, because when you divide 16 by phi, it would leave a remainder of 1. Okay. How is Fermat's theorem is applied in scientific calculations? So, currently what we have done is we have just explained the various theorems which are present, and from now onwards we will actually look at how they are applied and what is their application in the RSA. And there's a similar question from DCRU which says what is the practical uses of Chinese remainder theorem. So again we will actually show you when we are looking into the RSA algorithm as to how the Chinese remainder theorem will help us at one point to prove the correctness that RSA is indeed correct, and secondly we will also show that how the Chinese remainder theorem can be used to do a decryption in the RSA algorithm. Okay, so please explain the Miller-Rabin test. So that will be covered from now onwards. That's a primality test. Okay. Okay, so let's look more into detail about the RSA algorithm. As many of us know, the RSA algorithm was invented in 1997 by three cryptographers, Shamir, Rivest and Adelman, and this was one of the most popular public cryptographic algorithms at that time. So it has kind of revolutionized cryptography in a large number of ways, and it is also one of the most popular algorithms that is used in the internet and for almost every e-commerce application that we actually do a transaction on the internet. Okay, so let's look at the RSA setup or the particular setup which we actually visited in the last class. So we had Alice and Bob, who are like two people, maybe they are connected remotely by the internet and they may not even know each other, but they want to actually communicate with each other in a very secure manner. So what we seen in the last class was that Alice and Bob, let's assume, do not have a trusted source so that they can exchange a common key. So what they do is the following. So Bob would actually create something known as as a key pair comprising of two keys, KE and KD. KE is known as the encryption key, also called the public key, and KD is called the decryption key or the private key. So what Bob would do is that he would create this key pair KE and KD. He would keep KD private to himself, while he would make KE public on the internet, maybe publicize it on his website and so on. So Alice, who wants to communicate secretly with Bob, would take would go to Bob's website, pick up the KE which she has advertised, that is Bob's public key, and she would blast her message through this encryption algorithm with the public key to get the ciphertext. Now you note that this ciphertext is encrypted, and once it is encrypted, there is no way to decrypt the ciphertext unless you have the corresponding private key. This means that Alice, who does not have the decryption key, will not be able to decrypt her own message from the ciphertext. And needless to say, Mallory, who is actually snooping on the network and is able to actually retrieve the ciphertext, does not have the decryption key which Bob has, and therefore will not be able to retrieve what is the message contained in the ciphertext. On the other hand, when the message arrives at Bob's computer, Bob knows what is the private key corresponding to the public key, KE, and he would take this private key, pass it through a decryption algorithm along with the ciphertext to obtain original message what Alice had sent. Okay, so let us look at how RSA actually works. So the underlying assumption is, as we mentioned in the last week, was the fact that this particular problem known as integer factorization is extremely difficult. So this integer factorization could be considered as a one-way function, wherein suppose we are given n, which is a product of two prime numbers p and q, and assuming that p and q are very large prime numbers of the order of say 512 bits or 1024 bits, then computing the particular product p into q is easy to do. So given p and q, computing p into q just requires a multiplication, and therefore anyone can actually compute p and q easily if they anyone could actually compute n if they know p and q by themselves. Essentially, we just need to multiply these two numbers. So given p and q, it is easy to multiply. However, on the other hand, if you're given just n and you were asked to actually find what p and q is, then it is extremely difficult. So it is very difficult to actually factorize n into p and q, while it is very easy to multiply the two numbers. And this basic assumption is what is the central thing in the RSA algorithm. So keeping this assumption in mind, let us now look at how the algorithm RSA is actually works in this setting, in the Alice and Bob setting. The RSA algorithm in fact has a three-step process. First is the key generation. Then is the encryption, and then is the decryption. So the key generation is typically done by Bob. So what he would do is the following steps. So Bob would first select two large primes p and q, which are primes. And when I mean large primes, so a typical large prime would be roughly around 500 to 1000 bits, and then he would take p and q, and another requirement is that p should not be equal to q. He would take p and q and compute n equal to p into q. He finds the product of n into p and q, and he also computes the Euler-Tauschent function of n. That is, he computes phi of n. So we have seen that if you want to compute n, which is a product of two numbers p and q, phi of n will be equal to phi of p into phi of q. Further, what we also know that is, since p and q is prime, so phi of p is equal to p minus 1 and phi of q is equal to q minus 1. Okay, so this is the first step he does. The second step which Bob would do is that he would choose one random number b, which is in the range between 1 less than b and less than phi of n, and GCD of b comma phi of n is 1. That is, b and phi of n are co-prime to each other. And since they are co-prime, he can actually compute the inverse of b. So he can compute this element called a such that a into b mod phi of n is congruent to 1. Okay, so given these three steps, Bob would actually define the public key as the tuple n comma b, and the private key is defined as um, the primes p, q, and a. So this is what Bob does initially. He creates the public key and the private key. So as I've mentioned earlier, this private key is kept secret. That is, this tuple p, q, and a is kept secret, while the public key comprising of the value, the number n and the choice b is made public. Okay, so this is the first step, which is the key generation part. The next step is on Alice's side, where she will encrypt a message. So the second step is encryption done by Alice. Okay, so what Alice does is she goes to Bob's website and picks up the public key comprising of n and b, and let us say she wants to actually compute or encrypt the message denoted by x and send this to Bob. So what she does is that she takes x, raises it to the power of b, and does modulo n, and sends this particular value, which we call y, to Bob. 3, y is the ciphertext. Sent to Bob, while x was the original message. Okay, so this is the second step, and the third step is the decryption part, which is done by Bob. So what Alice does is the message y, which is the ciphertext, is sent to Bob. So Bob takes the y, which he obtains from Alice, and raises it to the power of a. Recall that a is the corresponding private key and does a modular n. And if the private key and n are correct, then this particular term will be equivalent to the message x. Now, no other person, no other attacker or any other third person on the internet who is able to capture what y is, but that person will not be able to do this decryption, because the assumption is that only Bob has the corresponding private key A, right? So pictorially we are just showing it like this. P and Q, and the encryption is done by taking the message x, raising it to the power of b modular n to give you y, and here what I missed is that x belongs to Zn. That is, x is a number from below n, less than n, and this y is the ciphertext, and it is sent to Bob, where he takes y, raises it to the private key a, does a modular n to get the decrypted value. Just to take an example, let us assume that the two primes are p and q, P has a value of 653 and Q has a value of 877. So what Bob would do is that he would select these two primes. These are much smaller primes. In reality, the primes would be much larger. And he would find the product of these two primes, that is n, equal to 653 into 877, that is 57 or 5,72,681, and phi of n, it is p minus 1 into q minus 1, that is 652 into 876, that is 5,71,152. Then Bob would randomly choose a key, a public key called B, in this case it is 13, such that the GCD of 13 and phi of n is 1. And from this he would find the inverse of B mod phi of n, that is 13 inverse mod phi of n, that is 571152, and he gets this to be 3,95,413. So this is the private key A. Okay, now in order to look at this, let's assume that we have a message called X, which is 12345. So Alice would take this message X, raise it to the power of the public key, which is 13, modulo the n, that is 5,72,681, that is this n value, to get 5,36,754. So this is the ciphertext which she obtains. Then this ciphertext is sent over the internet to Bob's side, where he takes the ciphertext, raises it to the power of A, that is 3,95,413, modulo the same n, 5,72,681, to get the original number 12345. So you see that on Bob's sides, when he decrypts the ciphertext, he gets back the original message 12345 that Alice had sent him. Now let us look at why this particular thing works. Okay, so we will look at the correctness of the RSA algorithm. Okay, so what we want to prove is that if you take y, raise it to the power of mod n, we should actually get the value of we should actually get the original message which was sent as X. So let us see what is if this is in fact true. So first, let us assume that GCD GCD of X comma n is equal to 1. That is, we are assuming that X happens to be coprime to n. Okay, and we have also seen that the corresponding ciphertext is obtained by computing y congruent to x to the power of b mod n. So this is done in Alice's side. Y is sent to Bob on the internet, and Bob will take y and raise it to the power of a modulo n. So this is congruent to x to the power of b power of a mod n. So this is congruent to x to the power of ab mod n. Now recollect that a into b is congruent to 1 mod phi of n. Why? Because if you go back to the original way we have created this key, we see that we have actually chosen A, which is the inverse of B, using something like the extended Euclidean algorithm, such that A into B mod phi of n is congruent to 1. And when we see this particular equation, what we can actually say is that phi of n divides AB minus 1. Similarly, what we can say is that some constant t into phi of n plus 1 is equal to AB, right? So this is from our initial theorems or initial properties of the modular arithmetic that we have seen earlier today. So therefore, we can now substitute t of phi n plus 1 to be a, which is equal to AB over here. So this is congruent to x to the power of t of phi of n plus 1 mod n. So this is nothing but x t of phi of n into x mod n. Now let us look at our famous Fermat's little theorem again, Fermat's little theorem, which states that x to the power of phi of n is congruent to 1 mod n if GCD of x and n is equal to 1, that is x and n are prime. So from here we can actually get that this is congruent to 1 to the power of t into x mod n, and this is nothing but x mod n. So you see that if you take the ciphertext y, raise it to the power of a mod n, where a is a private key, you will eventually get back the original message x. That is, we under the assumption that the GCD of x comma n is equal to 1, that is x and n are not are co-prime to each other. Now let us relax this assumption. Let us say that the GCD of let us consider the second case where the GCD of x comma n is not equal to 1. Okay, and let us see if we can actually decrypt the message properly in this case also. So this is our second case. Okay, so here we will make use of the Chinese remainder theorem. Okay, so recollect that in the Chinese remainder theorem, what we actually said was, suppose we have this number called n, which is, as we know in this particular case, n is the product of the two primes p and q, p into q. Then the Chinese remainder tells us that if x is congruent to y x to the power of ab mod p and x is congruent to x to the power of ab mod q, then it implies that x is congruent to ab x to the power of ab mod n. Okay, so we will use the Chinese remainder theorem to actually state that when you raise x to the power of ab mod n, we will get back the original message x, and we will actually prove it by showing that raising the individual message x to the power of ab mod p and x to the power of ab mod q, we will get the original message again. So recall that x to the power of ab is nothing but y to the power of a mod n, right? Okay, so notice that GCD of x comma n is not equal to 1, and the factors of n is either p and q. Therefore we can state that the GCD of x comma n is equal to p, or GCD of x comma n is equal to q. Exactly one of this has to be true. Why? Because the only two factors of n are p and q. Therefore, if the GCD has to be not equal to 1, it has to be either p or q, because only these two are the p and q are the only numbers which divides n. So without loss of generality, let us assume that the GCD of x comma n is equal to p. Right? We can of course prove the same thing if the GCD happens to be q also. So and what we're going to now show is that if the GCD of x comma n is p, then x is congruent to y to power of a mod p, and x is congruent to y to power of a mod q. Now y to power of a mod q is nothing but x to power of b a mod p. This is congruent to x to power of ab mod p. Now, since the GCD of x and n is p, this implies that p divides x, and as we know p divides n. So let's look at this part where p divides x. Therefore we have some number, let's call it as k, such that p into k equal to x. So we can now represent this particular thing as x to the power as x to power of ab mod p to be equal to some p into k to power of ab mod p. And so this is the right hand side of this particular equation, and as we see that because of the p term over here, any power of p into k modulo p should be equal to 0 because of this the p present over here. So if you take this particular number, this very large number p into k to power of ab, and find the remainder when divided by p, you will get 0. Similarly, on the left hand, so this is the RHS is of that particular equation is 0, and the left hand side, which is just x mod p, is nothing but p into k mod p, and this is equal to 0 as well. So we have the LHS equal to RHS, and therefore indeed that x is congruent to y bar a mod p when GCD of x comma n equal to p. Now let us look at the other equation. Okay, so we have proven this thing. Now let us try to prove this one. Okay, so it states that x is congruent to y to power of a mod q. Now one thing you would notice is that um, uh, since p and q are relatively prime, therefore the GCD of x comma q will be equal to 1, right? Because q is a prime number. Therefore y to the power of a congruent to x to the power of b to power of a, which is congruent to x to the power of ab mod q could be actually written as x to the power of p phi of n plus 1 mod q. So how did recollect that? How did we get this? So we are actually using this same notation what we have done previously, that a into b is congruent to 1 mod phi of n. Therefore phi of n divides ab minus 1, and therefore t into phi of n plus 1 is equal to ab, and we have just substituted the value of ab as t phi of n plus 1. However, we know that t phi of n or rather t phi of n is actually equal to t into phi of p into phi of q. Therefore, we can actually write this congruence to be equal to x to the power of t phi of p into phi of q into x, because of this plus 1 over here, and mod q. Now we'll apply Fermat's little theorem, but before that let us just rewrite this term much more better. So what we are going to say is that x to the power of phi of q t phi of p into x mod q. Now you see that since GCD of x and q is equal to 1, therefore x to the power of phi of n or phi of q mod q will be equal to 1. Therefore, this particular term is actually equal to 1. So it is congruent to 1 to the power of t phi of p into x mod q, and this is equal to x. So we also seen that y to the power of a uh, uh, y to the power of a mod q is equal to x. So what we have seen is that this equation as well as this equation has been proven. Therefore, from the Chinese remainder theorem, we can say that x is congruent to y to the power of a mod n, that is nothing but x to the power of a b mod n. And thus we have actually been able to prove the correctness of RSA not only when the GCD of x comma n is equal to 1, but also when the GCD of x comma n is not equal to 1. Okay. Now let us now quickly look at how to implement the RSA algorithm. How to actually implement the RSA encryption scheme. Okay, so we look at the RSA implementation. So recollect that, and to do an encryption, what Alice would do is she would take the message X, raise it to the power of the public key B mod n, and she will get some value Y, and on the decryption Bob would take the Y, raise it to the power of A mod n to give you back the original message X. Now how would you actually perform this particular encryption and decryption? Okay, so one thing you would notice that typically this value of n is of 1024 bits, 1024 bits number, and B is another number which is roughly of 1024 bits, and therefore one way of therefore just performing multiplication like x into x into x into x and so on is almost impractical to do. So we need a better way than to just perform this very naive approach, which can possibly through which you can possibly never do a single encryption. So in order to do this, what we will be seeing is a simple algorithm known as the square and multiply algorithm. Okay, so let us say that we want to compute uh, x to the power of b mod n. Okay, so the first thing that we do is we take a binary representation of b. So for example, if b equal to 23, then its binary representation is 1 0 1 1 1 2. Okay, and then we have this very simple algorithm known as the square and multiply algorithm, which will take the value of x, b, and n, and it will return x to the power of b mod n. So the working is like this. Okay, so first thing you do z, you just take a temporary number called z equal to 1, and then you have a loop for I equal to L minus 1 down to 0, where L is the length of this particular binary string. For example, over here L will be 1 2 3 4 5, L equal to 5 in this case, because there are 5 bits in this particular binary representation of 23. So do this, then you compute z equal to z squared mod n, and if bi is equal to 1, then you compute z equal to z into x mod n, and then finally return z. So essentially what this particular algorithm is doing is that we are traversing bit by bit of this binary equivalent of this particular exponent b, and in every iteration we are taking some variable called z and we are squaring it. Further, if the particular bit is set to 1, for example bi is the ith bit in the binary representation of b, if this bit is set to 1, then we also multiply z with x, and this is continued until you get 0, and then you return the value of z. So let us just check what is how this particular program executes. So we'll take I equal to some number, so that's the iteration. So I equal to L minus 1 initially, so I is equal to 4, and let's take the value of the bit bi, and let's take the value of z. So initially z equal to 1, and bi is the bit bi4, which is this top bit over here, so this is also 1. So what happens in the first iteration is that you enter over here, you take the value of z, which is 1, square it, and then since the value of bi is equal to 1, so you multiply by x, so this becomes 1 squared into x, that is x. Next iteration, you take I reduces by 1, so it becomes 3. Look at the corresponding bit over here, that is 0, and what you are doing is you're taking the z and squaring it. So z has a value of x, so you're squaring it, and you're not doing anything else because you're not entering this if loop or inside this if, because the value of bi is equal to 1 and this if will fail. Next iteration for I equal to 2, you have bi equal to 1. So as usual, you take the value of x and square it, so you get x power 4, and since you have 1 over here, so you enter into this if, and you multiply the value of z into x, so it is x power 4 into x, that's equal to x power 5, and then that's the end of this iteration, and then you have I equal to 1. I equal to 1 has a value of 1 over here, so as before you square, so x power 10 into x, this is x power 11, and the last iteration when occurs when I equal to 0 and the least significant bit of this is 1, so you again take the value of x, square it again, so you get 22 into x, so this is x power 23. So you see that after running through this particular square and multiply algorithm, for an input x, you get an output z, which is x to the power of b mod n. And you see that this running time is just as long as the length of the exponent b, and it's much more feasible to do. In practice, however, I think there are still more complexities involved in actually creating or implementing this particular algorithm, essentially because each of these values of x, b and n, as I mentioned, are very large. Therefore, what we actually use is something known as a multi-precision library, which could do all these arithmetic for as large numbers as possible, as is required. So one thing you could actually look up when you go back, and if you're further interested, is the multi-precision library called GMP, which is the GNU multi-precision library. And instead of doing just a square like this and a multiplication like this, which is typically not feasible when the length is of these x and z are very long. Therefore, we use this GMP multi-precision library to which is capable of doing arithmetic of any arbitrary long or large number. So this was how encryption was done. And obviously, since, as we've seen, since the decryption also has a very similar operation like y to the power of a mod n, so the similar square and multiply algorithm can be actually used to decrypt as well. However, when we're doing the decryption, we can make use of the fact that Bob, the decryptor, knows the factors of n. That is, Bob knows the p and q values. So let us see how this particular thing helps. So implementing decryption. Taking one trivial way and one obvious way from what we have studied about encryption is to do exactly the same thing, where we take y, raise it to the power of the secret key a mod n, and as we have proved before, this would be congruent to the message x, right? But given the fact that decryption is done by Bob, who knows not only the secret value of a, but he also knows the prime factors p and q. So given this, what can be done is that we can make use of the Chinese remainder theorem. So since we know that p and q are relatively prime to each other and Bob knows both p and q, so instead of computing this one where n is typically of size 1024 bit and therefore quite time consuming to actually compute, what can be done equivalently is actually compute x1 to congruent to y power a mod p and x2 congruent to y power b mod q, and then use the Chinese remainder theorem to actually derive this value of x. So we will not go further into detail about how the Chinese remainder theorem can be used to speed up decryption. Now, why do you actually achieve a speed up in decryption over here? So the advantage is that these values of p and q are typically half as long as the value of n. So typically the n and p and q values are typically of the order of 512 bits, and therefore the size of the arithmetic, the size of the multiplications, the size of the square operations and so on that we are actually doing in order to compute each of these cases is done on numbers which are half as long as when you're doing in the modular n case, and therefore we will be able to do both two exponential, this is y power a mod p as well as y power b mod q in much faster time than doing one single y power a mod n, just because of the fact that n is much longer, is twice in length as p and q respectively. Okay, so I'll take a few questions about about the RSA algorithm before we actually go into this very interesting property thing about finding primes. Okay, so I'll take a few questions for maybe 5 minutes or so. Why always RSA? So this is a question from a GECL. Why is RSA always done with prime numbers only? Is it possible to do it with any other way? Okay. So, like I mentioned, the problem with RSA is that you need to actually, or the reason RSA actually works is that we have this number n, but given only this number n, it is actually very difficult to actually factorize it into two numbers p and q, right? And if we actually take n to be, let's say, the product of multiple primes like p1 into q1 into r1 into t1 and so on, where p, q, r, t are also prime numbers, then it would actually relax or make the problem a bit more easier. Now, for example, if we want to actually factorize this uh, number n in the typical RSA case, we need to find either p or q, right? However, if n happen to be the product of multiple primes like p1 into p2 into p3 into p4 and so on, now factorizing means we would just need to find one of these primes, and which makes the task a bit more easier. So, so this is one reason. The second reason is that P and Q, as I mentioned, was prime numbers. And as we will see in the next part of this particular class, finding these prime numbers is not so easy. And therefore, if you are able to actually do an encryption with, or able to do our work with just two primes, why should we actually go for multiple primes, or in order to actually get the same amount of security? So that way, I would say that having just two prime, n to be a product of two primes rather than n to be a product of multiple primes um, uh, would have much more beneficial in terms of security, as well as in terms of from an implementation perspective. I hope this helps in understanding. Please demonstrate an integer value plain text 66. This is a question from AJCE. What if the key generation done with RSA and encryption is done with another algorithm? So one thing to actually note is that every encryption scheme has three aspects. One is the key generation algorithm, then there's an encryption algorithm, and then there is a decryption algorithm. So you change any one of these things and your entire scheme will not work. So if you're planning to use another encryption scheme, then you have to use the new encryption scheme's key generation, and the encryption algorithm and the decryption algorithm. You cannot actually mix and match from various things. Okay, so why do we choose always prime numbers? Basically, the fact that product of primes is difficult to factorize, and this is a well studied problem, and that's the reason we always choose prime numbers. So there's a question from another question from AJCE, which I really don't understand the question. So it is like, please demonstrate with an integer value plain text 66, which I don't understand this. So I'm just going to leave the question for now. Okay, so how the components stored as a single public key? So another question from AJCE is, how are the components n and b stored as a single public key value? So as I mentioned, the public key comprises of n and b, and the private key comprises of p, q, and what is that? PQ and the private key A. So there is no hard and fast rule about how to actually store these things. So one simple thing would be just to have a text file, and in that text file you could store the value of n and the value of b. Alternatively, in the case of the other side, you have another text file which stores the value of p, q, and the secret key A. So there is no particular format, at least there's no generalized format in which these particular keys have to be stored, except that you need to find some way to communicate that this is my private key, comprising of these two values n and a, n and b for the public key, and pq and a for the private key. So what are the weaknesses of RSA? So that we'll be looking in this class, mostly in the next class, where we'll be actually looking at some of the attacks on RSA and some of the weaknesses of RSA. So I'll pass this question for now, and we will take it up next time if it still persists. So there's a question from DBCET, Sudeep. So what is the range of prime numbers used in practical cases? So as I mentioned in this slide itself, so typically the size of the prime number is roughly 512 bits. So this means it is a very large prime. And why do you need such a large prime? Is the fact that we want it very difficult to actually be able to factorize this value of n into p and q. If the values of prime is very small, for example, let's say just a 32-bit or a 60-bit prime number, the size of the prime is just 60 bits, then possibly the attacker could by do a trial and error and then be able to factorize n into its prime factors. Therefore, we need to have these p and q values so large that the attacker may not be able to do a brute force search through all numbers and all possible prime factors, and it should be actually difficult for the attacker to do a trial and error attack and factorize the value of n. Is there so there's a question from IGCE PJB Talvidar. Is there any other alternatives for RSA? Yes, there are other alternatives for RSA. One very famous alternative is the elliptic curve cryptography. There is also the Diffie-Hellman, which is also quite famous, and there are other variants as well. So another question from GEKL, is RSA still used? Yes, RSA is used extensively. So probably every time you log in or your system, you most likely must be using RSA internally to actually maybe log into your various mail clients or the various websites, log into your bank accounts and so on. So it's still used very extensively, and probably I would say that every day all of us must be using RSA at least once. So this being said, there are the inherent limitations of RSA is that the size of the numbers are very large, like in this case 1024 bit is the size of n, and the size of p and q is order of 512 bits, and because of this, performing these computations like y power a mod n or y power a mod p, y power b mod q is extremely time consuming, and so therefore people are gradually moving on to other public key algorithms such as elliptic curves, where the size of the digits are much more smaller. So typically in an elliptic curve crypto system, the size of the digit may be around like 163 or 190 bits, which is almost like 5 to 6 times smaller than the RSA numbers used. So because of the smaller size in elliptic curves, so the size of the operations will be considerably smaller, and an encryption and decryption time will be much more quicker compared to that of RSA. How does RSA performs? So there's a question by DGI Gargi. How does RSA performs against brute force attacks? So the entire thing about the security of RSA depends on the fact that the attacker does not know P and Q, right? So what would happen if the attacker knows P and Q? So if an attacker actually knows P and Q, then what he could do is he could compute phi of P, which is equal to P minus 1, and phi of Q, which is equal to Q minus 1, and then he will be able to therefore compute phi of n, which is equal to P minus 1 into Q minus 1. Now he knows the public key part, which is B, n comma B, and he also knows that the private key is A such A, which is actually equal to B inverse mod phi of n. So in other words, and as we have seen earlier before, A into B is congruent to 1 mod phi of n. So now the thing is he knows this he knows this thing which is p minus 1 into q minus 1. Therefore he can compute phi of n. He knows b because it is public, and therefore he only requires to compute b inverse. So given these two informations, he can easily compute b inverse by the extended Euclidean algorithm which we have studied. So this being said, therefore if he is able to find b inverse, therefore he can compute, he knows what a is, and a is the private key, and therefore he can actually decrypt any message. So the entire security of RSA depends on the fact that this P and Q is kept secret. So if uh, if the value of P and Q is small, let us say you just for practice you keep a value of P as say 13 and Q as 17, then the attacker could possibly start to try all the primes starting from 2, 3, 5, 7, 11 and so on, until he actually finds some prime which works and which can factorize the value of n into uh, P and Q, and from there he can actually compute what the private key was, and using the extended Euclidean algorithm, and decrypt all the messages which have been enciphered or ciphered with that particular key. So to avoid such brute force, where the attacker always tries every possible prime until he finds one of the prime factors of the n, we keep the values of p and q very large, so that such trial and error types of mechanisms, or which we call as a brute force attack, will fail to work. I hope this is a nice question, and thanks for asking it. What is the computational complexity of RSA? So this is a question from DCRU Pavinder. What is the computational complexity of RSA? So by this question I mean, I think you're meaning what is the complexity of doing an encryption. So if we actually look at this square and multiply algorithm, which actually performs the encryption or decryption for RSA, you see that we have a loop from L minus 1 down to 0, where L is the length of the public key in terms of a number of bits, and therefore just by analyzing this particular loop or this particular algorithm, the encryption algorithm for RSA, we can actually conclude that the complexity or the time complexity is linear or polynomial in the size of the exponent. So why is RSA not popular now? So I've answered that question. What is the time taken to break the key size 1024 bit? So this is a question from Vijay Lakshmi from PECPY. What is the time complexity to break the key size of 1024 bits? So 1024 bits, if you have a 1024 bit key, so there is actually no, at least in the public literature, there is actually no known person or group which has actually been able to break the RSA, an RSA system which has a 1024 bit key. The best world record, or the world record right now is breaking the RSA, which has roughly around 750 bit key, has the key size of roughly 750 bit, or rather the value of n is 750 bit. And so how difficult is it? Just to give you an intuition, so it would typically take a very powerful supercomputer roughly around 3 to 6 months to actually break RSA of 760 bits. So if you actually go for 1024 bit, it will take much more longer. So, and that is the reason nobody has actually found a way to break such a RSA when it is of 1024 bit as yet. Although it is not impossible, and maybe in the next maybe 4 or 5 years you will actually see an attack on RSA 1024 bit, but right now it's extremely difficult. Why integer factorization is not easy in RSA? Okay, so So another question from Vijay Lakshmi. So why is integer factorization not easy in RSA? So why is the integer factorization not easy in RSA? So integer factorization is a NP, almost an NP complete problem, and uh, and there is no good solution for this, as we will see in the later part of the class, and therefore it's a very difficult thing. So there is no good solution or an algorithm or a deterministic algorithm to actually factorize integers, especially when the number is very large. So how large can be the value of P and Q? I have answered that. So typically it will be 500 bits for P, 500 bits for Q, and also we need the fact that P should not be equal to Q. So a question from CEKKL, is there a way other than square and multiply method to find the factors? So square and multiply is not a way to find the factors of n. So if you look at the particular algorithm over here, the square and multiply is used to actually take a value of x, which is typically the plain text, or it could be the ciphertext, and the square and multiply algorithm would simply raise the value of x to the power of b modulo n. So we are not actually trying to factorize n over here. It's just to do an encryption or a decryption. What are the applications of RSA nowadays? So I've answered this quite a bit, so I'll not answer this. Where is RSA more applicable, secrecy or authentication? So RSA is possibly, I would say that, okay, this is a question from DB CET Sudeep, where he asks where is RSA most applicable, for secrecy or for authentication. So by secrecy I mean it's for encryption or for authentication. So RSA as such is more usable for authentication, I would say, rather than for encryption. The main reason being that encryption is typically done by block and stream ciphers, which are much more efficient to actually perform encryption rather than any other way. On the other hand, for things like key exchange and for digital signatures, RSA or public key algorithms are used extensively. So there's a question from GECL Mohanjit. How does RSA keep itself from attacks? So like I mentioned, the entire strength of RSA is based on the fact that it is difficult to factorize the values of P and Q. And if tomorrow one of us actually, or somebody actually finds out a way to efficiently factorize P and Q, n into its into the products of P and Q, then RSA could be actually broken. Just to give you an example, so there is a lot of talk about quantum computers, which is likely to actually be invented maybe in the next 5 to 10 years. And on a quantum computer, factorizing the value of n into P and Q can be done in polynomial time, or there is a straightforward deterministic algorithm to factorize n into P and Q. And therefore, when quantum computers are invented, RSA can be actually trivially broken. And this is also the reason why people are looking beyond RSA or elliptic curves to actually find public key algorithms which are suited for quantum, or which can be secure even in the quantum computing environment. Okay, and so at least coming back to RSA and our normal systems, the entire security is based on the fact that it's very difficult to factorize n, and that is what is actually keeping RSA working for the last almost 30 years or 40 years now. Okay, so this is a question which is again I think similar. That's it. Yeah. So quickly, we will look at the next part of this particular thing. So I'll just give you an introduction to this. It's called like finding primes. We'll just start this and then we will continue on this particular work next time. So so first of all, why do we what, like we mentioned all along, so RSA depends a lot on prime numbers. So essentially what we had said that we needed to find this n, which is the product of two primes p and q, and p and q we have said is of 512 bits each. So p is 512 bits. This is another prime of 512 bits. Therefore, n is typically twice as long as this. So the n is 2 into 512 bits. So typically 1024 bits. And so as we mentioned, the first step in generating the key is to actually find such prime numbers p and q which are also different. So p not equal to q. So what is the problem in doing this is the following. So I'll just show you the slide. Okay, so essentially, how do we actually? We said that this P and Q is actually created or generated by Bob in order to create his public key. But how does Bob actually find out these these primes? So in our school days, or even at the start of our engineering, we've done this very common program, especially in a computer lab, to find out whether a number, say m, is prime or composite. So what we have done previously was that we have run a loop from, say, for I equal to 2 to m minus 1, and we checked whether like I divides, if this is true, then we know that m is composite. And if you're not able to find such an I, then we say that return m is prime. Right, so all of us have surely done some program like this in our first years or in our school days. And so for example, if we want to check that 13 is a prime, we ran our loop from 2 to 12, and each time we have actually divided that number I divided by or 13 divided by I, and if it divides perfectly, then we know that the number is not a prime because it has something which divides it, and therefore we call it as a composite number and immediately return. Otherwise, if we otherwise at the end of this loop we say that it is prime. Then much later we also tried a few tricks. Instead of going till m minus 1, we actually said that, hey, let's not go to m minus 1, but let's go till square root of m, and this would be sufficient for us to actually find out if a number is prime or not. And then a little more a better algorithm, what we had done previously was that instead of checking everything over here, we will only check the numbers which are prime. So instead of running a loop from 2 to 3, 2, 3, 4, 5 till square root of m, we'll run a loop for all prime, for I, for all primes I which is less than square root of m, right? And this also was probably a way to actually find out whether a number was prime or composite. So does this solve our purpose? So such a simple algorithm, so what is the big need to actually learn about this? Now the problem over here is that even if you look at the best of these three algorithms, which is this case, and we want to actually find out whether m is a prime, and m is typically of, like I mentioned, m is like p or q, and m is of order of 512 bits. Number of primes that are possible in this is extremely small. Okay, and it's so small that for example, if you have a 512-bit number, so we have to run a test all primes from 1 to square root of m, that is typically from I is less than 2 power 256, and this, so we need to check all values of I which is prime and less than 256, and this itself is a very huge and extremely difficult task. Just to give you a notion of how long this would take, on a single computer it would typically take around maybe at least 10 to 15 centuries if I have to run this on a laptop or a desktop. Therefore, these simple algorithms like the ones we have discussed will not be able to actually scale for prime generation for something like the RSA encryption scheme. Therefore, we need something better than just these trivial prime testing algorithms, and that's where we actually come up, we are going to study in the next class something known as randomized algorithms, where we'll be actually looking at some different types of randomized algorithms which will allow us to actually determine quite fast, quite quickly, whether a number is prime or composite. Okay, so with this I'm just going to stop for today, and we will continue on Wednesday, on today's 20th, so on Wednesday. Okay, thank you.